right? So my name is Danish Sajwani, and I'm from Blue Wave AI, and I've been working for Blue Wave AI for almost two and a half years now. I have a background with master's in computer science from University of Ottawa, Canada, and it's focused on artificial intelligence and machine learning. I've been in the software industry for almost more than 10 years now, with some background in telecom industry before, and now in the energy sector and transportation and all that. In the telecom sector, I worked on native cloud-based enterprise-grade software, which was deployed across the globe in probably all the different continents, 7 continents, and we had about more than 2 million plus active daily users using our software. And after that, I switched to Blue Wave AI with the climate change and everything that we are hearing about EVs and charging and infrastructure required for that. So I thought, AI company which is working on EV charging optimization platform. So I helped develop that platform recently at Blue Wave AI, and that's going to be the focus of my conversation today as well, which is about residential and EV charging, the fleet side of charging optimization as well. So what does Blue Wave AI provide? Blue Wave provides software as a service, cloud-based products, which are specifically geared towards enabling the efficient use of renewables, the energy storage, and EV charging optimization for the utilities, for system operators, for fleet operators, and independent power providers as well. It's an artificially intelligent software that provides optimizations and recommendations, and our customers report significant reduce in the net energy cost because of the optimization and the predictions that we provide to them. So the next couple of slides are about the energy transition that is taking place for the last several years now, and the challenge that it poses for all of us. And then I'm going to talk about the solution that Blue Wave AI provides for those for the transition as well as the challenge. So this one graph here on the left, and I know it's a little bit hard to see, so I'll go over it quickly. If we concentrate on the green line there, that's the line for the renewables. And we can see that from 2010 to 2022, that line is slowly increasing, and then it goes past the nuclear, which is in the purple, and then the coal later in 2022. And then the fossil fuels are at the top with orange and red line, which basically tells us that the renewables are being produced more and more now. And we see that the share of the energy produced from renewables is increasing. So that's one of the transition that is taking place. The other transition that we see on the right graph here is in the middle you see a vertical section that is for 2030, and then each of the lines mean the estimation that we did in, for example, 2018, and then 2020, 2021, and then 2022 for the EV market share that we would have in 2030. And so for the 2018 line, the first one at the bottom, the curve, that shows us that the estimation for 2030 was that we'll have a 21% EV market share. But if you look at the top line, which is 2022 estimations, that's a 53% EV market share by 2030, which is a huge difference, going from 21% EV market share in 2030 estimations to 53%, more than double, which basically means that we are seeing more and more increased use of EV adoption. And that trend is going to increase as we move along. And both these graphs are for the US numbers. So that's one of the transitions that is happening. Now, also what we see is these are some of the traditional ways of producing energy. So on the top right side, we see natural gas and coal and the fossil fuels. and then the loads that use that. So typically we would see households using it, industries using it, fossil fuel based EVs, sorry, not EVs, fossil fuel based vehicles using it. So that's kind of the model that we had traditionally. Now what has happened in the recent past is there is more utility renewable energy coming in, and then the local production is also happening, which is through wind and solar powered energy generation, and then battery storage of that generation as well. So what we have seen so far is, all of these solutions, the local loads as well as the production of the energy is changing slowly, and now comes the residential EVs and the EV fleet moving towards electric vehicles as well, and that puts a lot of load on the grid. As you can imagine that when the cost of the electricity is low in the evening, if in your neighborhood 50 people start charging their cars at the same time, your transformers are not going to be able to bear that kind of load. So that's a big challenge that we have, and at the same time, when the fleet operators are bringing in a lot of big fleets together and they want to charge them to be ready for the next day, let's say, for whatever, whether it's public transportation or school buses or taxi companies, they're all bringing in fleets now. So that's also a challenge for the grid. So renewables is one challenge, and then the other one is more load coming in. This is where Blue Wave AI comes in with its center and edge platform and the products EV Everywhere and EV Fleet Orchestrator. And I'm going to talk about both of these products a little bit more into the details in these next few minutes. And we can see that renewables are going to increase in the future, hopefully. And hopefully the natural gas and fossil fuels are going to reduce, as well as the consumption of that through the fossil fuel based vehicles is going to reduce as well. And all that to say that we will need an orchestration software to work on the connect to the production side of things as well as to the consumption, and that's where Blue Wave AI provides the solution, which is artificial intelligence based prediction models. It has optimization algorithms, and it has a modular architecture which is tailored for specific use cases, and I'll talk a little bit more about that in the next few slides. It's a cloud-based software as a service, which is flexible and scalable because it's built in a modular way. So we have three main products: Smart Grid Optimizer product, the EV Fleet Orchestrator product, and the EV Everywhere product. Let's look at EV Fleet Orchestrator product a little bit more in details. The main objective of Fleet Orchestrator product is to be able to do depot energy optimization. Based on the routes and the schedules that are fed into the system, coming up with the best way of charging so that we don't create peaks. And I think you were also talking about the peaks, and then you have to pay for the peaks as well. And that's exactly what we are working on to provide a solution for that, so that you don't create peaks. We can connect to the behind the meter battery systems to do optimization, and then interactive dispatcher dashboards are also provided, so you can interact with the software yourself. And then EV charging optimization and control is provided through the front-end interfaces. We can do load, as I said, peak shaving, but we can also do load shifting as well. So depending on what time of the day you want to charge, we respect the schedules and the routes, but we also can move the energy usage from higher demand time to lower demand time on the grid. We use OpenADR for demand response. This is where utilities come in, they can create demand response events, and then we can do optimization based on that. So here's the overall architecture of the platform. We have a center and we have edge. Center is mainly used for end users serving the end users. So it powers the dashboards, it powers data exploration, and whatever data you provide to it, it can visualize that for you. It can provide AI predictions for you. It can provide optimization and recommendations, and these optimization and recommendations can be manually done and actioned by the ground staff, or it can be actioned automatically by our software by connecting to the assets on the ground, which creates more data, and then you can explore that data through the dashboards. Edge is the back end of the platform, which is where the AI predictors live, which is where the optimizers live, and we've created a new concept of resource adapters, which connect with different kinds of assets. It can connect, so each module of the resource adapter can connect to one type of asset. We work with a company called SmartCar, which is based off of here in US, to control the EVs directly, and to control the chargers. We work with OCPP protocol and charger vendor specific APIs. So going into a little bit more into the deployment of EV Fleet Orchestrator, here are the 4 different types of inputs that you can provide to the software. You can provide routes and schedule data, real-time vehicle telematics, effective range of EVs, and how many chargers do you have, what kind of capacities those, what kind of power levels those chargers serve, the connected EV status to it, which is again used. We use OCPP for that purpose, which is a widely known protocol. And then real-time energy cost for any optimization that we want to do based on the cost of the time of the use. So providing all of that input to the Fleet Orchestrator platform, and including any manual input that the operators want to provide through the dashboards, plus some configuration based on what kind of equipment you have on the ground and the optimization objective you want to deploy. We get 2 outputs from the system. One is the optimal charging schedule based on the objective of the optimization that you pick, and the other one is visuals and insights as to what's happening on the ground, what actions can you take, and what recommendations is our software providing. So the next few slides are about some examples of how we have done this in the last few years. This is an example of a municipal transit depot with electric bus fleet. On the right, you see the graph where the vertical line with the red or orange section vertically shows the high demand time, and you can see that the charging, which is those bars in blue, is happening when the demand is also high, and it happens in the afternoon as well as in the evening, both times when the demand is high on the grid. So they asked us to optimize this for them. So we created a simulation for them with no optimization. So you can see that again, the times when they're charging are high demand times. And then we used the objective of tariff optimization, which is time of use. We shifted the we shifted the entire load towards the right. So that blue curve that you see, which is superimposed on the red one, which you saw in the previous one when there was no optimization, is moved towards the right a little bit. And you can see that more of it is falling under the green area now, and less on the red area. The area under the curve remains the same because the EVs require same amount of energy, but we have done load shifting here in this case. This is the example of peak shaving. You can see that the flattened peak here during the time in the evening, for example, when we have more time to charge and the vehicles need to go, early in the morning, then we can do peak shaving more than what we can do in the afternoon. So that second one that you see, we have done some peak shaving, but not that much because there's very little time in the afternoon after the vehicles come back from their first route in the morning, and then they have to leave in 1 or 2 hours again. This is an example of school bus fleet where it's a Canadian fleet bus operator. They have 600 buses and about 800 buses and 600 routes. They wanted to see whether it's feasible for them to buy the vehicles, electric vehicle, and electrify their entire set of routes with electric vehicles only. They're planning to have 10 plus sites for charging. So they wanted us to, run a simulation and see what kind of equipment might be required and what kind of budget is required. Do they need a battery system? What will be the return on investment on a BESS system or solar panels and things like that? So Blue Wave ran simulation for them. For energy use for all the routes, as well as the depot charging load optimization based on the objectives that I mentioned before, peak shaving and load shifting. And then we figured what we figured was more than 85% of the routes were actually possible to electrify with the kinds of buses that they were looking at. In the worst case scenario, and in Canada, you can imagine that the range of the temperatures is really wide. It's about 60 degrees between winter and summer. So, it's good to see that more than 85% of the routes can actually be served by electrifying them. And 5 times reduction in the depot peak charging load by using Blue Wave AI's peak shaving optimization. About 60% reduction in the cost, because what we were finding is some customers were really over provisioning their grid limits and paying for that as capital expenditure, but they didn't need to do that if they were able to optimize the use of electricity and not create peaks. 15 times operating GHG was reduced compared to the ICE fleet if they were using ICE fleet. This is example of taxi fleet in the Middle East. We are working there, and this was an interesting one. What was happening there is they shared their data, initial data, and they said, we are using EVs, but we don't seem to be generating a lot of revenue. Let's see what we are doing wrong here. When we looked at the data, and what was happening was the EVs were actually charging when the demand was high, and the trips were not being picked by the EVs, but they were being served by ICE vehicles. So we said, we are going to develop a charging recommendation software for you, and the goal would be to increase the EV utilization and of course the revenue because of that optimization, so that they are not charging during the high demand times, but they are charging before the demand time, because we can predict the demand based on their previous demand patterns, and then they are ready to pick up the trips when they actually appear. And we can have reduced carbon footprint because of that as well, and cost savings because of fuel and because of maintenance, because the EV miles driven are more. We saw 12% EV utilization more EV miles driven, and 12%, approximately 12% revenue gain by that customer. 50% less use of ICE kilometers driven that were previously missed by the EVs because they were charging at the time when the demand was high. So it was a win-win situation for us as well as for the customer. So all of that was for the fleet operators, and we looked at a few examples of what type of fleets we have worked with. This EV Everywhere product is mainly for residential customers. We have a front-facing end-user smartphone app that the users can download from the Apple Store or Play Store. We work with the utility companies here, or they can not sign up for utility companies. Both options are available. We do direct control to the vehicle for EV Everywhere using Smart Car, and we use Open ADR protocol for demand response events, which the utilities can create and the distributors can create. So this is the overall solution overview of EV Everywhere. So what we do is we generate peak electrical load predictions. We generate the peak demand predictions, and we feed it into our system that generates recommendations for when the demand will be high and when a demand response event can be created. So that gets fed into the system, and then the utilities can take that recommendation, they can accept it, which goes through our OpenADR system, and basically we can control the batteries inside a neighborhood, and also curtail power directly by pausing and resuming the charging on the vehicles. We provide system operator dashboard, we provide distribution utility dashboard that they can send and create DR events which can be accepted, rejected, or partially accepted by the system operator. And we also provide one other angle here, which is the OCPP. If we have some recommended chargers that we have set up at our office space, which we call the flight test center, and whenever we are doing software work, we first test it over there before it's ready to be shipped to the customers. So we have a few chargers there that are OCPP compatible, and we recommend that to the residential customers. If they install those chargers, then we can do OCPP control directly to the chargers as well, in addition to the vehicle control. Moving towards, probably this is the last slide here. Blue score is an interesting concept, and it's a new innovation that we have brought in. It's in the patent work right now. This is, to explain it in a very simple way, it indicates the optimal time for charging the EVs based on the real-time renewable energy generation and the electrical demand in the grid. So the easiest way to understand this is when the renewables are high, because we see energy mix during the day, right? Every hour you see energy is produced either by fossil fuels or through renewable energy or through other sources. And when the renewable energy is high and when the demand is low, blue score is high, which means it's the best time to charge. So we are using this concept across our product lines, and we are even using it with our customers as well as an open API, so that people can use this concept to say this is the best time to charge in this particular area or neighborhood, depending on if we have the energy mix available. We have several cities covered now that we provide blue score for, and we use that in our EV Everywhere product at the moment as well for charging optimization. So very quick summary of EV Everywhere product: intelligent EV charging. It provides demand response capabilities. It provides a user-facing, smartphone application, and a utility automation for the system operators as well as the distribution companies. And that's all. Any questions? Yeah.
Have you had any interaction with commercial truck fleets on these products?
Yes, so on that front, we have been working on package delivery with package delivery companies, and UPS is one of them, for example, in Europe, and we are in works with them in very early stages of our collaboration with them, and they have a similar issue. Interesting story there. When I was in Germany at one of their depots, they have just converted their bikes into package delivery vehicles, and it has portable batteries. So somebody or few people actually took the portable battery out and started charging like 4 of them on the same circuit, and then at night time when somebody plugged in the 4th one, the breaker stripped, and then they had an outage over there. Which is kind of what we are working on, right? When you connect something, it doesn't have to start charging right away, because you don't need to create so much load on your transformers and your circuit breakers. So if you feed the circuit topography to us, we'll be able to manage the charging for those customers and not rely on the fact that manually somebody connects more charging infrastructure or assets to the grid or to the local circuits. Any other questions? Okay, well, thank you.